Welcome. In this video, I will show you how to solve the finite square well in the case L equals 0. That is Griffiths problem 4.9 as it appears in the third edition of Griffiths' Introduction to Quantum Mechanics. The problem states the following. It says a particle of mass m is placed in a finite square well, which is a potential that is 0 if r is smaller or equal to a, and v0, some finite potential, if r is greater than a. So what we want to do now is find the ground state by solving the radial equation with L equals 0. And we want to then show that there is no bound state at all if v0 times a squared is smaller than this amount right there. Okay, it may seem difficult, but keep in mind this is not really different from what we have done before. And in fact, this will be very similar to what we saw with the finite square well a few videos ago. So if you haven't watched that, it is maybe good to just refresh that. Okay, so what we will do here is we will solve our radial equation for this region and for this region. Now the first region is the easiest, and we have done it a few times. I will do it rather quickly. So we have minus h bar squared over 2m, d squared u dr squared. Nothing, I'm just copying here. This is the radial equation, by the way. The potential is 0 and L is 0. So all of that is going to be 0. So we simply have this is equal to EU. Okay, and now we have d squared u dr squared. This is equal to minus 2me over h bar squared. Okay, and times u. So this we can just call k squared, and that way we get minus k squared u. Okay, so none of this should be new to you. We have done it many times before. This gives us the differential equation d squared u dr squared. This is equal to minus k squared u. Now this is the same differential equation as in the infinite square well, and we have solved it many times. So the way I like to solve it is just put everything to one side so that we get plus, and this is equal to 0. Now we just kind of factor this out. So we get d dr plus k, and the dr, since it's plus, we need an I. So plus ik ddr minus ik times u is equal to 0, right? I'm just simply rewriting. If you multiply through, you see that you get the exact same thing. And that way, if this is 0, I need that this acting on u is 0 or this acting on u is 0. So we get two differential equations. d dr u is equal to minus iku, right? This one. Or we have d dr u is equal to iku, which is coming from that one. So those are the two differential equations that will give us both of our solutions. So each one will give one. So from here, both of them are solved in the same way, right? So we just do separation of variables. So we get du over u is equal to minus ik dr. Now we integrate. So we get that the natural log of u is equal to minus ikr. And now we simply have to exponentiate everything. And we get that u of r is going to be plus some constant, of course. It's going to be some other constant a, which is e to the c. Right? A, this is e to the c. And e to the minus ikr. So I just did it very quickly. And from the other differential equation, we get that the other solution is going to be some other constant b, e to the plus ikr. So of course, the complete solution will be a sum of the two. U of r, this will be a e to the minus ikr plus b e to the ikr. And we can just write this from Euler's formula, using Euler's formula. I'm going a bit fast again because I've already done this in a few videos. If you're unsure, just go back and watch the initial videos where we solved the infinite spherical well. So just go to the infinite spherical well video, and I go into full detail there. Here I'm just telling you how things are done. So here you just use Euler's formula, right? E to the ix is equal to cosine x plus I sine x. I also have a video where I explain why these two representations are going to be equal. So we can just say a, which is not the same a as this one, but maybe let's call it a prime, times cosine of kr plus, this would be b prime, sine of kr. Okay, so you can do this. You can write it in terms of cosine and sine instead of the exponentials, and it is better because that way applying boundary conditions will be much easier. Okay, so whenever we have these just bound states in infinite spherical well or finite or in this spherical case, it's better to have cosine and sine. It's easier to work with. And since these are any constant, I can just simply rename them to A and B and forget about the primes. Okay, so that is the solution inside, but we have to take one more consideration, and it is that our solutions are actually not really U of R, right? Whenever this U of R is just this the intermediate step, because the actual radial equation, it gives us the solution big R of R, which is U of R divided by R. If you don't know where this came from, then I also have a video on that, and you have to watch that because you have to understand what the radial equation is and where it comes from, right? It's simply separation of variables in the Schrödinger equation from the theta and phi, the angles, from the radial part. That's where you get it. And we use this U as kind of just a useful function that we use here. So by doing this, we get A cosine of KR over R plus B sine of KR over R. Now the issue is that we want that inside of the infinite spherical well, our wave function has to be finite everywhere. So what happens in the limit, or in the limit when R goes to 0? What happens there? So let's take that limit of each one of these. So what happens to the limit when R goes to 0 of cosine of KR divided by R? So as this goes to 0, what happens? Cosine goes to 1, but R goes to 0. So this blows up, right? It just goes to infinity. So this is not acceptable. So for that reason, we need that A is equal to 0 so that this thing isn't there causing trouble. What about the second term? Well, the second term in the limit where R goes to 0, right, of sine of KR over R, well, this would just be, let's see, so sine goes to 0 and R goes to 0. So let's apply L'Hopital, right? L'Hopital's rule. So we have the limit as R goes to 0 of their derivatives. So that would be cosine of KR times K and divided by the derivative of R, which is 1. So this thing here is going to be just K. And the point is that this is finite. So this term is not an issue. So this term, good. Okay, that's good. So for that reason, U of R is simply going to be B times sine of KR. Okay, and this, well, this is of course inside. So let's now go to the other case where we are in the potential V0. Maybe instead of in and out, we should just say 1 and 2, but it doesn't really matter. So now we have to solve this, but when the potential is V0. So that means we have to solve minus h bar squared over 2m d squared u over dr squared plus vu, or rather v0u. This is equal to eu, right? This is still 0. Okay, so here we can just write it as d squared u dr squared. This is equal to, now we have v0 minus e, right? I am considering that we are multiplying by a minus sign, so we had e minus v0, and then we have to multiply by minus, so we get v0 minus e times u and times 2m over h bar squared. So that's what we have. Now let's call this thing, all of this, just L squared, using the same as before, right? Notice that the entire procedure is the same as before. We are finding the wave functions, applying boundary conditions is the next step, and then find the equation to determine the energy. Okay, so with that, we get d squared u dr squared minus L squared u is equal to 0. And how do we solve this? This is exactly solved in the exact same way as before. So we can factor this to write it as ddr plus L ddr minus L times u. So we can solve, I mean, this means that either d dru is equal to minus Lu, right, from this one, or the dr u plus, this is equal to lu. Okay, so those are the two equations that we get. Each one will give us a solution just like before. So this gives us that the natural log of u is equal to minus LR plus some constant, and now we exponentiate this, so we get that u of r in region 2 is going to be e to the minus LR times e to the c, but we can just call this e to the c, right? The exponential to any number is simply going to give us any other number. And doing the exact same thing for the other solution, for this one, we get the same, but with a positive sign, so DELR. Okay, however, this solution is not acceptable. Why? Because R can go all the way to infinity in this region, right? We're in the region where R is greater than A. So it can go all the way into infinity, and in that case, this blows up. You cannot normalize your wave function. So for that reason, D has to be equal to 0. Okay, it has to be equal to 0. All right, so that simply means that this thing goes away, and this is our wave function. Okay, so let's now recap our results. We found inside, or maybe let's just call it 1, that the wave function here is some constant b times sine of kr, and now in region 2, we see that it has to be c e to the minus lr. So let's apply boundary conditions, and there are of course two of them: continuity of the wave function and continuity of the derivative of the wave function. So boundary conditions. First, wave function, right? So continuity of wave function. So we need that at r is equal to a, b sine of ka has to be equal to c e to the minus lambda a. And then continuity of the derivatives, maybe let's do it so that we can see the wave functions. So 2, continuity of u prime, we get the derivative of cosine is sine, so we get b times k, so the derivative of sine is cosine, so cosine of ka, and then the derivative of this exponent will give us minus lambda c e to the minus lambda a. Okay, so now we must find some way to solve this, right? To get some sort of transcendental equation, like we always get in these sort of situations, so that we can graph it. So, well, the easiest way to get rid of as many complicated factors as possible is to take this equation, and so let's say this is equation 1, and this equation 2, so we take 1 and we divide it by 2, right? So we divide this part, so we get sine divided by k cosine, which is simply the tangent of ka over k, and then we have c e to the minus lambda a divided by this thing, so the c's go away, all we have is 1 over minus lambda. Okay, and we can rewrite this as k over minus lambda, or rather minus k over lambda, just putting the minus sign over there. Okay, so this is kind of our transcendental equation. Let's do what we usually do and just use a new variable, z, which will be the variable that we will be graphing and referencing here. So z will be ka, right? So that way we have tangent of z is equal to minus k over lambda. Okay, so what could we do here? Well, first of all, let's call k here z over a. That way we are going to have just this one variable everywhere. But now we still have lambda, and lambda depends on a whole lot of things. So we would like lambda to be written in terms of z. So what is lambda? Well, lambda, somewhere over here, we define to be 2m v0 minus e over h bar squared. So let's just plug it in. So we said lambda here is going to be 2m v0 over h bar squared, and I'm going to just separate these two, so we get minus 2m e over h bar squared. So this is simply lambda, I just didn't factor it. Okay, and why did I not factor it? Well, because this thing right here, this thing here is simply k, right? We defined k squared to be well, if I write it as squared, I don't need the square root. So this is 2me over h bar squared. So this thing here is simply k squared. So this is k squared. Okay, and now we have z over a. So this is the same as z. So z divided by this, and the a goes here. So we can just plug it inside, and we have then a squared there and a squared there. And now here we have z squared. So this thing here is z squared. And now the only thing that we have remaining right there doesn't depend on k or lambda. This is just a constant, and it depends on the parameters of our finite square well. It depends on the radius, a, and it depends on the strength of the potential, V0. Okay, so that means that we could just call this thing Z0, for example. So with this, we can write this as minus z square root of z0 squared. So yeah, so let's say z0 squared, sorry, that thing is z0 squared minus z squared. Okay, and another thing we can do is multiply and divide by 1 over z squared, or rather 1 over z, sorry, it will be squared once it goes inside the square root. So we get minus 1 over the square root of z0 squared minus z squared over z squared. So this part will be 1, so this is simply 1. And finally, what we can do is now multiply by this both sides and divide by the tangent on both sides, so that we get square root of z0 squared over z squared minus 1. This is equal to minus 1 over tangent, which is cotangent of z. And now this is a relatively nice expression to graph. And not only that, we have actually seen this already. If you go back to my video where we did the exact same thing, but for the infinite square well, we actually got to the exact same transcendental equation as this. So we have already even seen the solution. Of course, I'm going to go through anyways. So if we want to figure out what the solutions are, keep in mind the points of intersection C are going to be those that we are interested in for our possible values of the energies. So here I'm graphing in terms of z both of our functions of z. Okay, so we have both of our functions of z. Now, what about the cotangent? So keep in mind the cotangent of z is simply cosine of z divided by sine of z. Okay, so that means that if we are right here, so let's go for some important points. So pi over 2, pi, of course, this is simply a sketch. 3 pi over 2, then we have 2 pi, 5 pi over 2, and 3 pi. Okay, so at 0, cosine is 1, sine is 0, so it blows up. So we begin at either infinity or minus infinity. Because cosine is positive, we're going to be dealing with the positive infinity. However, we are not graphing the cotangent, we are graphing minus cotangent. So that means our function will be coming all the way from minus infinity. We go through 0, and then it goes to infinity at pi. And then again, it goes from minus infinity, 0, pi, minus infinity, 0, and so on. Okay? So this in black is f of z is equal to minus the cotangent of z. And now we have the square root. So keep in mind, the square root, we have a whole range of possible values of z0, right? It depends on v0, the strength of the potential, and depends on a, the radius of the potential, right? So of course, we don't really know exactly what z0 is, so there are several possible curves. But we do know the general behavior of this function, because we have this, when z is 0, right, we have basically infinity, a very, very, very large number. So we begin somewhere over there, right, somewhere at infinity. And then as z increases, this number becomes smaller until eventually it will just go to 0. right, at z0 equal to z, when we get to that point, this will be 1, and that will be the lowest possible value because we can't really go to negative values of the square root. So that means that we have a maximum value. So we will just go down and fall off somewhere, right? Maybe there, maybe it's going to go like this, maybe it's going to go like this, maybe it's going to go like that. Exactly how fast it's going to fall depends on z0. And all of those red lines are f of z is equal to the square root of z0 squared, z squared minus 1. Okay, and notice here something very interesting. If this function, right, if the value of z0 is not enough and our function just decays like this, it doesn't actually get to cross this function in the positive region, which is of course what we're interested in here. So in this region, we just cannot have a solution. Before pi over 2, there is no solution. Okay, that's very interesting. And the first solution is going to happen somewhere close to pi. So the first possible solution, which is the ground state, happens somewhere between pi over 2 and pi. Where exactly depends on the strength of the potential. So what we are saying is that if this square root decays before we get to pi over 2, then we just don't have a solution, right? We do not have an energy. So what does that mean? That means that if we are to the point here where we know that it goes to 0 when z0 is equal to z, right? That's what we were saying. And it goes to 0 when this is 1, and that happens when 1 minus 1 is equal to 0, and that happens when z0 is equal to z. So the minimum possible value, right, that we can have, the minimum possible value allowed is when z is equal to pi over 2. So that means that z0 has to be greater than pi over 2. However, what is z0? z0, as we defined here, is 2mv0 a squared over h bar squared. So just plugging in what z0 is, we have that 2m v0 a squared over h bar squared, and the square root of all of this has to be greater than pi over 2. So maybe let's just square all of this, and we get pi squared over 4. Okay, and from this, we can see that v0 a squared, which is of course what you can control in this problem. In principle, you can say what is the radius of the spherical well and what is the strength of the spherical well. That has to be greater or equal to h squared pi squared divided by 8 m v0, 8m a, let's see, just 8m because we want to keep that there, right? So h bar squared, yeah, just 8m. Okay. And well, we can just quickly, to make this thorough, find the energy as well, the minimum energy, because we know that k squared is equal to 2me over h bar squared. So that means that the energy is going to be h bar squared k squared over 2m, which is going to be h bar squared over 2m times z squared over a squared, right? Keeping in mind that z is defined as ka. And what is the smallest possible value for z? Right? What is the smallest possible solution that we found? Well, that means, of course, the smallest possible energy will come from the smallest possible z, which is pi over 2, right? So we saw that is the smallest possible solution, so pi squared over 4a, which means that the smallest value for energy is h bar squared over 8ma pi squared. All right, so that is the smallest value for the energy, and we can see that the condition that we found is exactly what we were asked. Yeah, so v0a squared has to be smaller or equal to pi squared h bar over 8. Now there's just a little bit of a difference in terms of how we wrote things, because the condition is that there exists no solution if z0, so no solution if z0 is smaller than pi over 2, right? Which is why that's how the condition is written in the here in the head of the problem, right? So there is no bound state in that case. Of course, what we found is that this v0a squared has to be greater than that expression, but of course it's the same, right? There can be nothing smaller, or it has to be greater. It's the same, right? So yeah, there we go. I hope that this video was useful to you. If it was, please make sure to leave a like on the video, comment and subscribe, and maybe even consider checking out my Patreon. So I'll see you in another video. Thank you very much for watching.